Mars has an average atmospheric pressure of 0.007 atmospheres. Would it be easier or harder to drink from a straw on Mars than on Earth? Explain. Well, it's kind of a difficult question. If you've only got 0.007 atmospheres, it's going to be easier to make a vacuum out of the straw. But with that atmospheric pressure, the liquid isn't going to rise very high in the straw, right? I mean, this is the way the straw works. You have your drink, you have your straw, and you suck on it to create a vacuum, right? You take all the gas out of the straw, the air. So here on Earth, with one atmosphere of pushing down on an evacuated straw, you get the liquid rising to a height of 700 millimeters high if you're talking about mercury, right? If it's milk, it's going to be even higher because milk is a lot lighter. On Mars, you only have 0.007 atmospheres pushing down, so easy to evacuate the straw, but your liquid isn't going to rise very high in the straw, right? I mean, this is what pushes the liquid up the straw, how much atmospheric pressure we have pushing down. 3, consider a sample of gas depicted here. What would the drawing look like if the volume and the temperature remained constant while you removed enough gas to decrease the pressure by a factor of 2? Okay, so if the volume and the temperature are constant, right, this is what it comes out to mathematically, right? V over T, right, temperature is constant, volume is constant. This means that the pressure of gas is directly proportional to the number of moles of gas. So if I want to halve the pressure, I'd have to halve the number of particles in the container. So this is how it would decrease the pressure by a factor of 2. Suppose you make a mercury barometer using a glass tube about 50 centimeters in length, closed at one end. What would you expect to see if the tube were filled with mercury and inverted in the dish? Explain. Well, the way the Torricellian barometer works, right, you have atmospheric pressure pushing down on the evacuated tube, and the height of the mercury goes up to 760 millimeters of mercury. So if you had a 50 centimeter tube, that's only 500 millimeters. So with a small tube like that, you're just going to fill it. It'll be filled to the top, right? And it won't be allowed to go up to 760. I guess if it's skinny enough glass, it'll break. Calculate the number of molecules in a breath of air whose volume is 2.25 liters at a body temperature of 37 degrees Celsius and a pressure of 734 torr. Well, this looks like we're plugging into PV is equal to nRT to find moles of gas. Once we find moles of gas, then we can find number of particles of gas. So the first thing is get that pressure in atmospheres, right? PV is equal to nRT only works if the pressure's in atmospheres and the temperature's in Kelvin. So add 273 to that 37, right, to get it into Kelvin. They gave us the volume in liters. That's good. So liters will cancel, atmospheres will cancel, Kelvin will cancel. I'll be left with moles. They wanted to know the number of particles. So for every mole, you've got 6.02 times 10 to the 23 particles. So you've got less than a mole, so you're going to have less than 6.02 times 10 to the 23. B. The adult blue whale has a lung capacity of 5,000 liters. Calculate the mass of air, assuming that the molar mass of air is 28.98 grams per mole. All right, so a mixture of oxygen and nitrogen, that's what it's going to come out to. Contained in the adult whale's lungs at 0 degrees Celsius and 1 atmosphere of pressure. Okay, so that's cold, but all right, so we're inside this cold whale. If the air is behaving ideally, again, PV is equal to nRT. It can be rearranged to solve for how many moles of gas we're collecting, and then we can use molar mass to go from moles to grams. So again, they gave us the pressure in torr. Oh, no, they didn't. They gave it to us in atmospheres. We didn't need this. Let me take this out of there. Absolutely not necessary. Delete. Let's go back up here. Wasn't in Torah. They gave it to us in atmosphere, so I can plug right in, right? They said I had 1 atmosphere, 0 degrees Celsius. That's 273 Kelvin. So all it is plugging in the 5,000 liters, right, to figure out how many moles of gas that would require, moles of air. The molar mass of air is 28.98 grams per mole. Convert it to kilograms, because this is going to be a lot of air. And yeah, you got 6.46 kilograms of air. You never think of having a fistful of air, but that would be a heavy amount of air, right? That whale would be breathing in its one breath. 78. Indicate which of the following statements regarding kinetic molecular theories is correct. For those that are false, formulate the correct version of the statement. All right, A. The average kinetic energy of a collection of gas molecules at a given temperature is proportional to m squared, or m to the 1/2 power. M, I guess, stands for mass. No, but that's going to be false, because average kinetic energy is proportional to temperature. So increase the temperature, right? We don't change the mass of our gas. We change how fast they're moving. So temperature would be the thing that kinetic energy is directly proportional to. B, the gas molecules are assumed to exert no force on each other. Well, that's right. So they're so spread apart. The idea is that gas molecules in an ideal gas don't feel each other. They're too far apart to feel each other. C, all the molecules of a gas at a given temperature have the same kinetic energy. No, that's false. It's on a distribution. Some of those molecules have very low kinetic energy. Some have a very high. Most of them have a average, or a most probable kinetic energy. The volume of gas molecules is negligible in comparison to the total volume in which the gas is contained. That's right. So the way we visualize this is, because the particles are so small, they don't decrease the volume of the container they're in. E, all gas molecules move at the same speed if they're at the same temperature. No, that's false, right? Again, it's on a distribution. So when you talk about a certain temperature, you have most of the molecules moving at a most probable speed, some moving at high speed, all right, and there's more opportunity for moving high, and some moving close to 0 Kelvin, right? So that's the Boltzmann distribution.